Okay, so last time we looked at the register. So today we look at the register file, how we can construct register file, which is including the many registers. Okay, so for instance, in the MIPS, there are 32 registers. Right, 32-bit register, and there are 32 registers. So let's try to construct register file which has 4 registers. Okay. So we have register here. 32-bit, 1 register, second one, third one, and last one. So this is, each one is a register. And then it has output, 32-bit output. Okay. And we have to support a register which is like this, add $1, $2, $3. So which means that this add instruction is reading 2 register contents, which means that if we are selecting, we have to be able to read 2 register value at the same time. So which means that we need to select one of them, we need mux. Mux. In this case, the input is 4 cases and selecting one of them. So which means that for the selection, we need provide 2-bit. Okay. So the first one, for the first one, we have to give some selection bit. So here in this case, $2 is selected, which means that we have to give 10 value as a selection. And also we have to read $3, which means that we need another box. Then there is selection bit. And output is 32-bit. Okay. So by adding these 2 mux, we can support 2 input read. And then what we have to do is we have to update the output of register 1. So which means that we have to selecting one of them. So for each register, there is load signal. Load. So if load is 1, that means the register is updated. So we have to selecting one of them, like a demux or decoder. Using demux or decoder. We are selecting one of them. Actually, demux is better. So this is the destination register address, and this is whether this is right or not. Light signal. So if light is 1, and then the destination selection is 0, 1, that means the 0, 1 register will be updated. Okay. So right value signal is 1 when we are using the register type operation, or load instruction. If we are using the store instruction case, then the raised one, the write value is not enabled. Okay, and then the content, which is 32-bit, is also provided. So this is data in. This is 32-bit. So that is also collected. Okay. So this is the raised file. Okay. So if we are looking at the outside of this circuit, then there are two output, which is 32-bit, and one 32-bit, which is for the data in, and also destination and first source and second source. So each one is 2-bit in this case. If we are supporting the 32 registers, then how many bits we have to assign for each test and source 1 and source 2? If we are supporting the 32 registers, so 32 means is it 2 to the 5? So we need 5 bits for each one. Okay. So most selection bit should be 5 bit. And also there is write enable, write signal. Okay. So this is data for write. And this is A and this is B. Okay. So this is raised file. Okay, so then let's try to construct this raised file using the logsim. Actually, we have to draw the 32 registers, but that is homework. When you have to do at this moment, you just create 8 registers. Okay, so we are just supporting the A register in the register file. Okay. To support A register, we have to use register. So there is a register. And so which one is 32-bit? 32-bit register. Okay, and there is data in. So this is a value to be stored. Okay. And this is enable. And this is clear. And this is outcome. Okay. So this enable should be 1 if we want to update the content of this register. So to support that one, write the signal is here. So this is this one is, and this write the signal is going to the Tmax. And how many bits we are supporting? So 2-bit. No, this is 1 bit. And selection bit should be, if we are supporting A register, selection bit should be 3 bit. So here this is enabled and this is selection. So both are enabled. Okay, selection should be input off. So this is the right of then the first one is first one. So we have to create um, okay. So we are finishing for the right one and box is required. Selection off. Similarly, you have to create another one. And then there is output. Which one is a little bit. Yes. And also we have to provide selection.
그나마만 엄청 많고 다른 거는 네, 없어요. 네. 그나마 다행입니다. 그나마 그나마 다행이다.
보여주세요.
사진이
재미나요.
있어서 다행이다.
아,
그리고 그냥 그나마 다행이다.
So first one is so this is 8-bit register. 8 register bar. 8. So can you draw this register file now? Right, is enabled. If you're creating new one, here, test. This is for the writing data. And this is A. This one is P. And there's a selection. It. A. And also C. So C is actually writing it. And then if we are providing that, here we have to provide class. Okay, so then you can see that if we are changing the address, then different is coming out, and right is disabled, even though, and this is not writing. If write the signal is 1, then there is something error. I don't know why. Maybe there is some connection error. So anyway, this is register file. So what you have to do is you have to create 32 registers, okay, inside of this register file, and then make this symbol, which is register file. Okay, so you have to do that. Okay. So now let's look at the next one. So we are finishing how to we can implement register file. Okay, so register file just including many registers. That's all. Okay, so now we will look at how to make a memory, RAM and ROM. Actually, using this register, we can also make a RAM and ROM because RAM is just including many registers. That's all. Okay. So here is the tri-state buffer. Then you didn't know about that. So let's look at what this gate is. Okay. This one has 3 output value. So normally we have a 2 output, 0 or 1, right? Every logic has 2 values, 0 or 1. So this is 0, this is 1, then output is 0. Okay. So tri-state buffer has 3 output, 0, 1, or high impedance. High impedance means that the circuit is kind of disconnected. Okay. So this is representing the high impedance. So for instance, circuit is like this, it's connected. And then we are measuring the voltage here, okay? If the voltage here, the point of D is 0 case, 0 voltage, then the B part, B will be 0, right? If D is 1, then B is 1. Okay, so voltage is like this. But what about the switch is open? And there is nothing here. Then what's the voltage of V? So it's not 0 or it's not 1, right? It's just disconnected. So this is the voltage of V is called high impedance. So the utility of this one is like this. If we are connecting the circuit like this, so we are just interconnecting and then measuring the voltage over here. So this is 0, this is 0, and this is 1. Then what's the voltage of V? That's the voltage of V. We know that this is disconnected. Right? So we don't need to think about this part, only we are just looking at the last line, which is 1. Okay. 0, 0, 1. So now this is open, this is closed, and this is open. Then what's the output of V? This 0. Okay. So the other way means open case, we are saying that this is high impedance, and this is 0, and this is high impedance. So 0, high impedance 0, high impedance. In this case, high impedance part, we just ignore it. So it's 0 value. And this one is also, left case is also high impedance 1. Then if we are reserving, then it is 1. Okay, so for the high impedance case, we just ignore it. Okay, so using this high impedance, what we can do is we can make a multiplexer, a DMUX very easily. Multiplexer very easily. MUX. So for instance here, in the previous case, MUX. MUX is a selection. So there is, let's look at the MUX. MUX is a selection of the two. So this is selection, and this is output, A, B, C. So selection is 0, then C equal A. Selection is 1, then C equal B. That's the MUX, right? Using AND OR gate, we can make this MUX. And also we can make a MUX using the tri-state buffer. So how we can do is, so this is a little bit. How we can do it? We are just using the 32-bit tri-state buffer. And this is A, and this is B. And we are the selection of one of the input. So selection. If this is negated, and this one is just connected. And just connected, that is C. So if selection is 0, that means the A part, this is enabled. So A is coming out, and B part is high impedance because it's like a disconnected. So C is just equal to the A. Selection is 1, then the lower part is selected. So C is like a B. Okay, so that's the how the tri-state is working. Okay. So in sometimes we will use this tri-state buffer to design the circuit simply. But anyway, in the Logisim there is a LAM already. So let's look at how we can use the LAM. So let's go to the Logisim. So let's try to continue on. LAM and ROM test. Let's Okay, so here in the memory, there is a two things. There is LAM and also LOM. Okay, so there is LAM. Okay, so here you can give some parameters. Let's assume that this is 32-bit. Okay, 32-bit. So, and then data interface. There are two things. One is synchronous load store port. Another one is asynchronous load store port and separate load store port. Okay, so you can see that the figure looks different. Okay, so synchronous load store port means that the data, it can be output and also it can be input. Okay, And also there is a clock. Synchronous means that there is a clock. Okay. So this data part can be input and output port. For synchronous case, there is no clock. That's the difference. And the separate load store port means there is an input port and there is also output port. Okay, so we will use this last one, separate load store port. Okay, so here, and also you can give the data width, address width. So 8 bit means that 2 to the 8, which means that 256 word can be stored in this memory. So let's give data first. Sorry to bit. Just connect it to the part. And also let's give the address. Mention that we are just using 8 bit. Okay. So if this is 0, then the first one is selected, first word. If this is 1, the second one, this is 3. Okay. So if we are changing this part, then we can selection one of the memory line. And here the output. To it, it's connected. And there is a store signal. Okay, store signal. 0 means it's not store. Selection means we are enabling this chip. So default value is 1. So it's selected. And this is clock. And load. Load is 1, then there is output. If load is 0, then actually the output is not there. Okay, so it's not enabled. So default value case, we assume that it is always 1. And clear means we are initialize this memory part. So let us assume that this is gonna be not used. Okay, so we are only using this store. And clock is here. So now let's test. Let us assume that the address is 1. So the one, this one, 0, 0, 0, 0, 0, 0, 0, 0. So that is 4 byte. Okay, 4 byte. So let's try to write. This is 1, last byte is 1, and this is 2, and this is 4, and this is 5. Okay, so let's look at what is happening. So store is enabled. And then if we are giving the clock, then you can see that this is changed. Okay, and because of this address part, that one is chosen. Okay, is given out. And if you are giving some another one, 0, so 0 output. Okay, so the data is not written because when the clock is writing, at that moment the data is stored. So clock is, then the data is written. Okay, so that is how the RAM is working. Okay, so you have to remember that we have to use the separate load store port. Okay, and also given the bit width and address width. Okay, so can you draw this lamp and then can you test it? Okay, so then let's try to use the ROM. Okay, so there is ROM. So maybe you already know the LAM is stand for the random. Yes. So you can change the data in the LAM, and ROM is okay. So this is a read-only memory ROM. ROM case you cannot write the data. So you just give the address, then it is generating the data. Okay. So here, mention that this is 32-bit output. And ROM is there is 256 word, and you can edit the data. So if you're clicking it, then you can see this is hexa editor, right? So here, one you can give is that I think this is eight. No, this is so you can give the value 1 by 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 16 byte. Okay. Like this. Okay. So you can save it. Or you can also load. Then if you are giving the address, okay, so can you try to draw this loan? So now because of some bug, sometimes exciter is not working. In that case, I think you have to restart the logism. Okay. So, okay. So now you are understanding about the ROM and RAM, right? So we also learn about the bugs and registers. So this memory-related component is called sequential logic. So this memory-related one is called sequential logics. Okay, so by combining combinational logic and this sequential logic, we can make processor. Okay, so how we are making the processor. So the goal of our processor is first, we have to support this kind of instruction. Okay, so what do we have to do to support this instruction? Let's go to the next chapter. So next chapter is chapter 4, which is designing the processor using this combination logic and sequential logic. Okay, so now what you will do is using the logicsim, you will create MIPS processor. Okay, so we will not implementing all the instruction. So simply we are supporting subset of instruction. So we will support add instruction, subtraction, and or settle on less than, load, store, branch, jump, and add I. Okay, so these instructions we are supporting. Okay, so to support this instruction, let's look at what is happening. So first, so there's this processor and there's memory. What do we have to do first? We have to give address. Okay, so first we are giving the address, then there is an instruction, some data. So that is loaded. And then processor is decoding of this instruction and then do something, right? So that's the how process is working. So what, let's assume that the memory is also inside the processor. So then what's happening is, first the CPU is generating the address. So this address, which register is containing this address in the CPU? So that address is in the PC register, program counter. So program counter is pointing the address that we are currently executing in the memory. Okay, so program counter we have. So when we are designing the CPU, we have to first implementing instruction fetch, which is reading the instruction from the memory. So instruction fetch using program counter, and program counter is generating the some address, and that is given to the memory address. Then there's the data. So actually this is ROM. Then that is stored in the register, and we are decoding. So this is 32-bit, and this is decode. So from this 32-bit, this is first register, this is second, and this is destination. So each one is 5-bit. And then this value is provided to the register file. And also, we know that this is some control signal also we have to generate. And then there is a output of data A and B, which is 32-bit. Then for this red register value, we are applying some operation. Okay, this is ALU. We have to give some function selection depending on what kind of operation. So the function is also provided from this 32-bit using some logic. The function is selected, and then there is output, and this can be updated to the register file. Okay, so this is a simple add instruction. Okay, so we will implement this kind of processor in the next time. Okay, so we will implement each one. So first we'll implement this part in the next time. So insertion patch. Okay, so we'll implement this part. So during the class, we can implement this insertion patch, but the implemented register file, it takes a lot of time. Okay, so this can be homework. We have to design this register file. So I think we can, if it is possible, maybe we can implement this much in next class. Okay, so next class we will look at how we are implementing this insertion fetch part, and then this insertion decoding part, which is reading register values. Okay, so anyway, you have to remember that how to use the register and how to construct register file, and also how to use lam and ROM. Okay, so we will use this component in the next class. Any question? No question. Okay, then see you on Wednesday. Bye.